So let's look at light as a communication medium. This is the most important slide. It looks boring, but actually every single keyword here has a long story behind it. So I tried to summarize them, and I'll try to walk you through the pros and cons of the thought of using light as a communication medium. Let's start with the pros. So as I said, it's unlicensed. Sounds simple. Again, long story. In Germany, in the early 2000s, all the operators nearly went bankrupt because they spent so much on the auctions when bidding for the 4G network. The spectrum was so incredibly expensive, it almost killed them. Right? Very successful for the government of Germany, very happy, but it stifled the market until now. So people like Deutsche Telekom, they're still paying off the debt they got on the licenses. No interference, is there spectrum, but how much spectrum did they get? 20 megabits, 20 megahertz here, 20 megahertz there for LTE? Not much. They nearly went bankrupt, right? So licensing is often an overlooked thing because, again, you're researchers, professionals. It's not really something that comes to your mind, but actually, if you say light is unlicensed, you have the attention of all the operators because they're saving, that minute you say that, they're saving a lot of money, right? So this is probably an underlooked but extremely important commercially or from an industrial perspective, extremely important an important aspect. It's free, right? Who doesn't like that? Not only that, it's unregulated. What does that mean? Every piece of spectrum, remember that horrible chart? That's actually a product of people working in regulators like FCC, Ofcom, or anyone in Europe who are taking that resource, the bandwidth, and they're managing it, and they're saying, okay, in this part, this will happen, in that part, someone else will be using it in this and that way. And there is a couple bands where everyone's free to use it, subject to some very, very mild assumptions, such as maximum transmit power, such as maximum duration of a single transmission, some kind of grab time. And that's called regulation. It's very annoying because even those little mild assumptions on maximum power or the duration of your transmission or the way you access the medium still has massive technical implications. So if you think, let's say, about the free bands, Wi-Fi works in them, right? I need to first listen before I talk on each of those bands. Sounds simple, but it designed, that essentially meant that the Wi-Fi design is based on some kind of CSMA-CA effectively random access scheme, which is extremely inefficient, doesn't scale. So a minor assumption or kind of requirement on those bands rippled through the design and made entire technologies non-scalable, for example, right? Or limits their potential, their range. I don't know how many of you try to, extend Wi-Fi coverage, but we wouldn't get very far, 200 meters maybe, and that's it. So regulation is another important thing. If light is not regulated, I'm not aware of any regulation other than eye safety, right? I can do whatever I want. No one's going to tell me what to do. And again, this is very important because you don't have any design constraints. In the Wi-Fi, we do a lot of IEEE standard in Nokia, so it's all driven around regulation. Someone said 20 years ago something that made sense at that time, doesn't make it anymore. They didn't even properly define what is it. For example, transmission on a single antenna shouldn't exceed milliseconds. Well, how does that apply to MIMO? Is it one antenna, all antennas? Is it distributed area? If I synchronize, are antennas at the end of the campus that are not synchronized or are synchronized still part of one complex or not? It gets very complicated nowadays. Nothing of that type is in the light spectrum, yes.
Are there any negative implications of it being completely unregulated? Like,
interference,
chaos. Every company has their device doing whatever it likes, like the implication of interference.
Interference, that's the only thing.
Okay.
Someone will jam you, you turn on the microwave, your Wi-Fi goes down, finished. You like that? Probably not, the video's buffered, right? You don't really feel it. But if you're in a factory where you have 5 nines of reliability requirement, because again, every minute of downtime costs you a fortune, it becomes a serious problem. But then you need to say something better than just, let's regulate across the entire country with one rule. Let's maybe have a little zone here where I, as an owner, say what's going to happen and design a network my way. It's way more flexible, right? So yes, the consequence is interference and it's bad. Nothing will work. But let's say local control is better than centralized governance 20 years ago, right? So regulation is still needed. There is areas that are critical, radars for airplanes, those things will be never touched. But if you start moving into areas where it doesn't really matter, where local owners could manage their works, well, we should probably be given the freedom. So that's what's happening in the 60 gigahertz, a lot of lobbying for opening up that space from tight regulation. Light, you don't need to bother. So again, there's a lot of people trying to make what you just said happen. Free access to spectrum, reasonable regulation, reasonable amount of collaboration. If you leave it completely distributed, it wouldn't work. So you again need those kind of allocation servers to ensure some kind of technology, some infrastructure. Someone needs to govern that. Free market will never work. It will be chaos, everybody pushing for the interest. We've seen it with Verizon and Apple and all the other guys trying to kill each other just because it's a power play, right? So regulation is important, right, but moving fast is also important. So, okay, so we said it's free, no one will bother us, and there's as much as we want. Now, this is a bit deceptive statement because I can say, oh, I am in the whatever multi-terahertz bandwidth. That means I have multi-terahertz of usable communication bandwidth for delivering my data. That's not true. You're still limited by the speed of your microelectronic component. So every LED diode has a little bit of capacitance. It's limited in speed. So the question is, how far can our technology bring us? But there's no ceiling, right? We can go as far as we can, right? So I've seen multi-gigabit diodes that can modulate at very low powers with very low biases. So research is moving really, really fast in the electronics industry, and we're getting serious bandwidth here, right? And if you again look at the Shannon formula, it's a it's a linear relationships, and I am not limited any way. I can expand and try to simply push the technology as far as I can in order to get the biggest benefits. I am not bound by 20 megahertz bandwidth in LTE, meaning that I design my network around that, because again, I can make it now ultra cheap. If I know my bandwidth is limited, I can start making it cheap and efficient around that constraint, right? So these simple statements make a lot of impact. LTE is all designed around the fact that it's 20 mega only. And if you start doing carrier aggregation, you start shooting yourself in the foot with those old ideas, because suddenly you can't do as much as you wanted. You don't have maybe power, the amplifiers are under design, the processing time is too low, So it's good to know that from the very beginning that there's no upper bound on performance. It's simply as much as we can deliver, right? So you start looking at fundamentals only. Power versus range versus bandwidth versus coverage, so the basics. There's no regulation. So it's a nice predictable system. That's very important, right? If I design something that works today, will work tomorrow as well. RF interference. This is something that sounds very straightforward and trivial. Light doesn't interfere with legacy radio frequencies. Sounds like a no-brainer, but actually it's, again, very, very important thing. I don't interfere with legacy systems, and they won't interfere with me. We're orthogonal, we can deploy, we don't need to worry. Half of Nokia's income versus costs coming from deployment and planning. If I go to an operator and I tell them, look, I deploy with a carrier-grade reliability network, I need to plan a lot. There's a big building standing between me and the mast and the users. People are getting phone calls. Verizon's not happy. They're calling, the coverage is poor, so Nokia gets fired or gets the heat from the operator, right? So planning and all the modeling and everything and interference, it's really important. It's a boring job. It's really important though, right?
I may say this is true as long as you use light as for the uplink. Otherwise, it's a different story.
I was going to say there's a catch to this. Sun and any of our own technologies are still interference. We're not free of any interference. But the worry about deployment and backward compatibility to legacy system is not there, right? It's our own interference and sun. Don't forget that sun is the source of strong interference. So that's what will bring us kind of here. Indoor, it will probably work very well. Outdoor, we need to be a bit careful. Still workable. There's a lot of work out there that's operating over optical frequencies out there. Now, let's go a little bit to more advanced features. So this was very straightforward. Free, unregulated, unlimited, backward compatible, deployable, right? What can you do with the fact that light has really, 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 really tiny wavelength? Well, sensing. That's one of the biggest trends nowadays in the wireless industry. Can I just use my access, I'm not going to call it radio access technologies, wireless access technologies, for anything else than just communicating? Could I, for example, have a radar that scans, gestures and face expressions and all that stuff from my access points and deliver extra functionality such as, I don't know, gesture commands or intelligent location or let's say kind of medical services where I monitor patients remotely, elderly people and so on in aging societies. That's one of the very interesting applications. And provide a sensing functionality alongside communications, and with very, very high resolution, wavelength typically limits or fundamentally limits the sensing capability that you have. If I have a 30 centimeters wavelength in, let's say, low frequencies, then I can resolve things that are at that order, right? I wouldn't resolve face expressions. Whereas with light, come on, we have cameras, right? So let's go infrared, not to annoy people with privacy issues, and start delivering these features. Could work very well. And there's a lot of demand for that. So it's an advantage. Very small wavelength can't really push the sensing capability very far. And if you remember, one of the mission statements of Enlightenment is to provide that sensory capability. So this is an interesting, how would I say, opportunity, right? Sensing, thanks to the small wavelength. Infrastructure. So what I said at the very, very beginning, some of you probably may have missed it, is that there's a revolution in smart industry, smart lighting going on, and light emitting diode-based lighting is being placed, and a lot of smart features are being developed, such as on-demand change of color tone, or monitoring of room occupancy and adaptation of lighting intensity, or simply control of lighting infrastructure for energy savings. That all requires those endpoints to be communicated over Ethernet or whatever other fiber optics, something of that type. That means there is communication infrastructure deployed. The bag hole, as we like to call it in our company, is there, and all I need is just the front end and the handsets, right? So a big part of network costs are actually, how do you actually then forward data from the access point all the way onto the internet, right? Costs you money, it's very, very expensive, it's huge. Again, simple example, to have a properly trained guy who can follow all the safety procedures, climb to the ceiling, open it up, replace the bulb, and come down, will cost you hundreds of euros. Now imagine he will have to deploy it, open the whole ceiling up, deploy all the cables. It's very, very expensive, right? So the fact that you have it there in the ceiling already, you can reuse, in a way, let's say smart infrastructure that's used for enlightening, is a great plus, right? So integrating lighting with communication is not a completely crazy idea. Half of the costs that you would be facing down the road, or deployment hurdles. I mean, come on, imagine you go to a company and tell them, guys, I'll deploy this great technology, but it all means that I'll open a ceiling in all floors and I'll be annoying your workers for 2 weeks. We're remodeling our office in Dublin now, so I can tell you it's annoying. So maturity of technology, optical technology is not something completely new. We have a lot of silicon and microelectronics solutions. So we already have the basic components, photodiodes, amplifiers, LEDs, and they're very efficient. 70–80% is not unheard of. It could be maybe more sooner or later. So this is very nice. We're not starting from scratch. We're going to build up on a 10–50 years of the results of microelectronics industry, right? So it's really around the design and the protocols and the solutions. The key components are there. They may be very expensive. They're not produced on mass scale, but they're there. That's what matters, right? Let's look at the cons. So as I said, interference from sun or outdoor in general might restrict us to indoor spaces. Not a big deal though, because 80% of traffic comes from indoor. So, and most of the people, most applications probably would be in residential or enterprise scenarios, again, indoors. So it's a con in a sense that we don't have the full deployability, the kind of the opportunity to deploy anywhere, anytime we want. But it's still a relevant case. It's most of the scenarios that are important. If you're close to windows, maybe it will be a bit tricky, but in general, I think the indoor aspect of light communications, or the kind of tendency to deploy things indoor, is not really that critical, but we need to be still aware of it, right? It kind of comes back down to the interference. Propagation, though, is way more serious, right? Light, as you know, doesn't really travel through walls. If I put my phone in the pocket, the transmission is kind of cut. So this is the most interesting pro and con at the same time. Pro in the sense that I don't interfere with nearby neighbors, con in the sense that I don't really have a good range. So now I need some kind of, spatially reused techniques that allow me to keep connections. This requires a lot of thought. It's an advantage and disadvantage. I'm putting it here into the cons area because there's a lot of serious implications that are not easy to solve, right? So I would say probably we would be more annoyed by the nature of light propagation than seeing some kind of security aspects, a la me being in the room, communicating, and no one hearing it outside. So I think that's very niche. It's interesting that people listen to that proposal, but I think it's a small thing, that the kind of permutation of what you could do. There's more kind of complications with, not being able covering entire campuses, for example, with light communications, right? And the last one is about the ability of concentrating energy that is transmitted to small areas, and again, increase the signal-to-noise ratio, as we remember from our formula, to deliver faster communications. We can't really steer light beams or focus them, narrow them down as comfortably as we can do with antenna arrays. This becomes a big problem on the uplink because the more, imagine it's a kind of dilemma between coverage and functionality. If I have very wide beams, I can on the uplink, when I transmit data back, I can maybe reach randomly deployed nodes with good reliability. The accessibility, reachability of the base stations is there, but the signal strength, the rate array will be very low. If I start narrowing down, maybe I design with lasers and I know where the access points are, then I start having problems with medium access. If I start transmitting, the neighboring nodes don't hear me. That means our two beams can collide. We have this hidden exposed node problem as we had in Wi-Fi in an unresolvable way. This is a fundamental problem, right? Now, what do we do with that, right? So this is one of the serious challenges to which, I don't know, I don't have an answer. Maybe my colleagues do, but it's a tough one, right? So, yes?
Scheduled access.
I know, yeah. But that means there is a mastermind. Everybody's synchronized, talking to each other. That means it's a workaround, but I have now way bigger, fatter infrastructure. Costs, complications, reliability, so it's a con. Agree. This is the only way, scheduled access, yes. What else, right? But that means maybe up to symbol level synchronization, right? Now, how fast are you? How long is your symbol? As the question, right? To what level do you wanna synchronize? If I have, let's say, soft handover, right? I wanna move on. I can push it this way. I wanna be mobile, right? And the faster you are, the more multi-gigabit speeds you have, the shorter our symbols, the tougher this approach is. So again, it's a limiting factor. That's all I wanna say. I'm not saying there's no solution, but it's a limiting factor you need to be in mind. What do you want? What is the system you're talking about? Maybe scheduled access on a per packet level is just great. Maybe I want a self-handover infrastructure for the entire factory with 5 lines of reliability. Well, then I really need to be very careful here, right? So it's a thing to keep in mind. I'm mentioning as a property of light that will drive your design. Okay, let me go quickly. I think I'm running out of time. So a couple challenges. Dimming flicker, well, not really a big one. Human eye perceives, let's say, up to 2 megahertz of flicker. Depends on the condition. Stroboscopic effects could be around those 2 megahertz. 25 is the standard video refresh rate for eye not to really notice. Could be done, but again, if you start talking about dimming and low intensity, low energy, it can start becoming a design constraint. Mobility is more interesting, right? So I'd like to have a mobile network. Everybody loves mobile networks. People would like to roam, maybe in a limited area, factory flow, robots moving around, but still keeping connectivity beyond simple access cones with little cone coverage is an interesting challenge. Uplink, as I said, probably the toughest one. How do we resolve the uplink problem? We don't have an uplink proper, fundamentally well-sounding uplink solution. So now I come to the customer and tell them, guys, I can do downlink, it's amazing, but I don't really know what to do on the uplink. I need to integrate maybe with RF. So it starts kind of losing the appeal, I don't really have a full solution. So this is a big challenge. Scheduled access, yes. So now how will it exactly look like? How many parts of the ceiling I need to open up in order to deploy my solution? Interference, well, this is a standard thing, really. Nothing new in wireless engineering. Wireless engineering is basically about power and interference control. Not much, right? So the fact that it never goes away keeps us employed. That's the good news. On the other hand, dealing with this is very annoying. It's constant struggle against interference. Line of sight propagation. Light is really directive and dims quickly. It fades away. You can still keep your connection maybe under the table in shadow, but it's slower. So if I say I would like to provide something better than throughput, nobody cares about throughput really. Bandwidth is here, it's a commodity. Let's talk about latency, right? So that means I need to have continuous coverage. I can't really go down because then data gets buffered in buffers. I start experiencing some latency spikes, or I even lose coverage, right? So reliability. The minute I have these constraints, and they're here, right? Let's say in an industrial factory, I'll talk about it later, you'll be asked ridiculous number of nines of reliability. A packet a year may not get lost just because the factory wants it. They'll pay for it, but I need to do it on a technical level. I need to be careful with this. Can't lose connection. Now, how do I do that? Light fades quickly away, right? So there's shadows, right? So an interesting challenge, not a problem, but challenge. Okay.